All right, so in this discussion, I'm going to go over some aspects of what distinguishes geographic data from other data. As always, I like to start off the discussion with a map. This is an interesting one. It's the most popular spectator sports in the world. Um, the, I'm sure you can guess without, at least some of it, you can probably guess without looking at the legend, but the green, as you can see, that's actually soccer. They call it association football, but that's what we call soccer. And the blue, you might guess also, is hockey. There's only two countries in the world that do hockey. And then Gaelic football, I found that one interesting. And the Republic of Ireland, that's kind of their national support. And any of your cricket, uh, Australian football, which I don't know much about. Anyway, maps are cool. They answer a geographic question, and that is a geographic question. Um, all right, so here's an overview. We're going to go over basic aspects of different organizations that you may encounter or you will encounter in this class, and then go over the sort of the difference between data and information systems and database management systems, and then go over some examples of how GIS can help these database management systems, how they can basically make spatial analysis more easily. And then we'll go over a little bit about data quality, like accuracy and precision, a little bit, just an overview of GPS systems or GPSs, and how we actually get our geographic data, and then a discussion of feature and feature classes, and then a review of raster and vector. Okay, so in terms of organizations, there's a couple that you'll encounter in this class. Two of the really big ones are Esri, which they're the ones that manage and have created the GIS software that we use. So ArcGIS Online and ArcGIS Pro are both Esri products. They're really the industry leader in GIS. I think they've been around since the early 90s, but you'll see a lot of content from them this semester. They have a great YouTube channel. They have a website, Esri Academy, which you have access to if you're a Delaware Tech student in a GIS class. I have links to all that in the course, and I suggest you use them as you try to learn. We'll use data from USGS or the U.S. Geological Survey. Um, so they're a federal organization. They're part of the U.S. government, the Department of the Interior. They do a lot of things. Obviously, they manage sort of the geologic information about the United States, but they provide a lot of the GIS content. So the satellite data that you can use in GIS, and we'll use a little bit in this class. But anyway, USGS, it's a good source. If you ever see USGS, definitely valid data, one of the best data sources that you can use. But you'll see that here and there. Okay, so data, we talked about the importance of data. Data are the lifeblood of GIS. Again, we've talked about this before, garbage in, garbage out. And so you want to just be careful about the data that you're using. A map can look great, but if you use bad data, the map is either no good or it's not going to be as good as it could be. But keep in mind that we cannot perfectly represent what's going on in the real world in a map. There are always some assumptions made. It's necessary. You're basically doing it's kind of like a statistical process where, like if you're drawing a road line, for example, you're not following every little curve in the road, but you'd be as accurate as you can. Major turns you'll put in there. A lot of this depends on scale. Like, are you looking at a national map or a local map? The resolution or the sort of how accurate your features are on your map kind of depends on your scale as well. But just keep in mind that we're always going to make some assumptions because the world is too complex a place, right? And we can't measure everything. Um, so in terms of some terms that sometimes people use this interchangeably, but I want you to think about these terms in this way. So data are the sort of like that's the core of a GIS. So we're using data all the time. That could be spatial data, it could be table data, it could be attribute data, but that's the sort of fundamental components of a GIS. Information is sort of how we put data together to answer a question. right? So if you think of this as an analogy of making things, making goods, data are like your natural resources, like your raw resources, oil and uh, whatever, trees, plastic, minerals, whatever. Um, that's sort of like your data. Like it's what you need to put together to make a product. And in this case, the product is information. So when we try to answer a geographic question, like if we look at our previous map where it was what are the primary sports watched by each country in the world, we need to take the data, put the data together um, into information. And then we use an information system to analyze the information. And GIS, remember, is Geographic Information System. So GIS is an information system. So what an information system does is it takes all the data, it takes data, puts it together into information, and then it sort of integrates, analyzes, visualizes, etc., that information. Okay, so that's an information system. It's like taking all these different, so each layer in a map, like a road layer and a city layer and a geology layer, population layer, whatever. Those are all pieces of information, and you put them all together in one system, and that's your makes a GIS. Okay, so I want you to take a look at the map and just pause it and think about this. This is just from Google Maps. As you can see, it's most of Newcastle County, Delaware. And think about what are some data that are used, what inaccuracies are there, any assumptions made, what information is provided, and then what information system is used. So go ahead and press pause and think about that. Um, and I'll go over some of it. So data, there's a lot of data here. Obviously, there's road layers. There's some, it looks like land use layers with you have your forested land, open land, more urban land up here. There's obviously some city data in here because you have Newark and Wilmington and so forth. There's some neighborhood data. You got some hydrology in here. You got some political boundaries in here. So there's a lot of data that are used to make this map. And of course, we're making assumptions here because, again, to use our example of roads, like the road doesn't exactly follow this path. There's little curves and so forth that you make assumptions. The river, the boundaries of the river aren't exactly this, but they're, obviously they're really close to that. So there are some inaccuracies here. And then the information, remember, is the putting of the data together. So the information, there's a there's a lot of information here. One is what are the major highways that go through Newcastle County, Delaware, up into Pennsylvania? What are some of the land uses in Newcastle County area? Where more information is what are the location of some of the cities and towns in northern Delaware and so forth, right? So that's all information. And then the information system, in this case, it's Google, so there's a GIS here that is the actual information system that's putting this all together. So anytime you see a map, there has to be data by definition, and there has to be information, and it uses, in this case, we use an information system, which is the GIS. So database management is a really important aspect of GIS. And here's one definition of GIS. This is from your reading, a computer-based tool to help people turn geographic data into geographic information, right? So you take the data, you put it together to provide information. And so how does a GIS store that data? It's all in tables. Okay, so we've talked about this before. Everything behind a GIS is in tables. And then, of course, there's coding that go into it as well. But in terms of how it's actually sort of organized is in tables. So you're going to be seeing tables a lot this semester. You've probably already noticed that already. And here's an example of a table. So a database in GIS, when we refer to a database, it's really a collection of tables. Um, and then so we have data that are in tables. We have a collection of tables. It's a database, and then we have a database management system, which is what a GIS. Part of what a GIS is it's a database management system. So it can take any number of tables, store and organize them, analyze them, query them, integrate them, etc. So you'll be doing a lot of that throughout the semester. Okay, and some key terms to remember for tables. So remember, a field is a column. Okay, so these are all fields here, field, 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 field. The record are your rows. So each of these individual, um, in this case, features is a record. So there's 7 records here, or 8 records here actually, because we started 0. Um, then you have some operations, and there's a lot more operations we can perform, but these are examples. You can do a query, which we've done already, union, intersection, and difference. So in order to perform database analysis to compare more than one table, you need to have what's called a common key, or just a key sometimes. So in other words, if I'm trying to match up this table data with another table, I need a way to compare them. I need to know which records I'm comparing. In this case, the key is the FIPS code. So this is each county, and this is a table with counties across the United States. Each county has its own FIPS code. So that's its code. Um, and FIPS is I can't remember what it's called, Federal Information Processing Standard, right? So this is not something that ArcMap makes up. This is actually, if you look up federal FIPS codes across, in the United States, these are known identifiers. So if I'm taking this table and comparing it to another table with counties, and I want to know how to match up the county, it's going to use the code. Okay, so it needs a key. Some other terms that are important to remember. You have your geometry in a table. So if there is a geometry, so if it's a shapefile, um, which is going to be a point, line, or a polygon, it's going to tell you whether each of those records is a point, line, or a polygon. And then they have to have an ID within the table. So this is your key, that's sort of an identifier that's a known, again, it's known nationally. This is assigned by ArcMap. So when you create this table in ArcGIS, it assigns it an ID, and that's just a way for ArcGIS to identify it. So it could be FID or an OID, which is object ID, but there's always an ID that GIS generates to identify fields. Again, this is not universal. This is just this table. This key is actually universal, right? So it's important to understand all of those terms. So remember, as I said, that we're always making assumptions, right? We can't measure everything. So really what they're doing is they're sampling data. So when we have our vector data, which we've talked about before, these are all shape files. We have points, lines, and polygons. And so a point, which all of these individual points are all points, right? These orange and blue. That's the fundamental unit in any shapefile. What I mean is lines are actually just points that are connected with a line. So in order to make a line, you need to have points. And then a polygon is just a line that connects to itself, right? So if we start the line here, we draw all these points, right? We're going to draw a line, draw a line, draw a line. And then if we connect it back here, it becomes a polygon, right? But that's all based on points. So points is really the fundamental unit. We put points together, and we get a line, and then we put a line from end to end and make it continuous, and that's your polygon. Okay, so those are all shapefiles. And you remember a raster is a grid, okay? And that is irregular intervals. You have a square of a certain size, and these squares are called pixels. And the size of the pixel is the resolution. So one of the standards for a really um, small scale map or with large pixel sizes is 30 meters. So if this were one of those 30-meter maps, then each side of the square would be 30 meters on the Earth. And so obviously we have to make an assumption because this is not a perfect square. So this is actually this image in raster form. And you can see how the line does a pretty good job of representing this road here. But the pixel, you're stuck with the resolution, and so it's going to be pixelated in some way. And that's a really good example of how you have to make an imperfect assumption when you create a raster because you can only pick one color per pixel. And so it's necessarily going to be rough unless this is actually representing an exact 30 by 30 square in the real world. You always make an assumption. And so that's one of the issues, as we'll see. One of the downsides with raster is you often lose some of the accuracy of the shape that you're drawing. Okay, but these are really good for continuous data. Okay, so that's some aspects of vector and raster, and just to give you a sense of how helpful GIS can be in terms of analyzing data. So if you had this stream, right? So this is a line, I have a shapefile with lines in it, and you want to just create a 100-foot buffer. So you want to find the area that's exactly 100 feet away from all parts of the stream. So basically what you would need to do if you did this by hand is you would have to draw a whole bunch of lines that represent 100 feet that are perpendicular to the stream, right? So ideally you would actually basically draw infinite lines in order to get the perfect shape. But really what you would do is you would draw, lines at selected points and then connect the dots from there, right? And then you could put together a buffer. So this would be a 100-foot buffer, and we'll do buffering later on. But this is a pretty common function of GIS, is to create a buffer. So that would take a long time to do by hand, you can imagine. But with a GIS, this takes a couple of seconds, and you just say, I want a 100-foot buffer around this stream, and it'll automatically generate this. Like, I mean, it's instantaneous almost. Okay, so that's an example of how easy a GIS makes vector analysis. Now, here's a really cool example of raster analysis, and this is what's called a viewshed. And so what a viewshed does is it tells you, you pick a point on the map, and it tells you either what you can see from that point on the map, right? So if you're on like this is a 3D rendering of a city, and if you're on top of this building here, if you're on top of one of the buildings, you obviously can see a lot of the city, but there's certain parts that would be blocked. And whatever's blocked is not in your view shed. Okay, so the view shed is a term that refers to what you can see. Now, you can work it the other way as well and analyze, if you pick a spot and you can use a GIS to analyze where on the map would you be able to see that point, okay? And so this is a really cool demonstration. There's no sound here. So, but what this does is it shows you, um, you could use this for a security purpose, where if you have, whatever, there's someone, a political figure, or there's a parade and there's somebody in a car on a parade going down the street, and you can analyze, okay, where could, if you're worried about assassination, you can say, okay, where can this car be seen as it drives on this road? And you can see that it identifies those points as the car drives. So you can see how the lines move. And then when it turns to purple, that means it's blocked by something. In this case, it's blocked. It's maybe hard to see, but it's blocked by this building. From this person's perspective up here, this building blocks it, so they actually can't see, right? But from this building, they could see. So that would be very, very difficult to do manually, but with the GIS, you can basically do it in a matter of seconds. Now here's a full view shed, and this actually shows a helicopter flying through a city. And it shows you the blue is what the helicopter can see, and the purple is what it can't see. All right, so as it flies through, again, that would be really, really difficult, and then it turns to green and red. Not sure why, but it goes to green and red because you can just change the colors. So just imagine how difficult that would be to do by hand. But with the GIS, you can do that really quickly. Now that involves raster data. That has X and Y and Z values. So raster data that has elevation. So again, this is something you'll encounter, and it's pretty easy to do with GIS, but it's very, very difficult to do by hand. Okay, so that gives you a sense of some of the things you can do with the GIS that sort of makes your life easier when you're doing spatial analysis. Now to some other issues relative to the how good a GIS is at representing what's going on in the real world. So two important terms to understand: accuracy and precision. So accuracy is exactly what you probably think it is. It's how close what you're seeing is to the real value. Whereas precision is uh, sort of how close the measurements are to each other, and to like how I mean I hate to use terms, but how precise are your measurements? So how many decimals can you go out to? Um, and I like these illustrations; they really help. So for something that's here, okay, so if you're shooting arrows at this target and you get a cluster like this, that means your precision's good because all of your measurements are close to each other. So it looks like your instrument is calibrated to the point that it doesn't make a lot of errors relative to itself. The problem is this is not accurate because we want to be closer to here. And so this is both accurate and precise. So they're clustered together and they're close to the right value. Whereas this is off. This is pretty accurate. I wouldn't say this is great accuracy, but it's at least closer to the bullseye. But it's not precise because they're spread out, right? So there's some error within the instrument itself that is not allowing it to be super precise, but we are getting close to the real value. Whereas something like this, you're all over the place and you're not clustered together, and so it's neither accurate nor precise. So precision, we normally look at the significant digits, so how many decimal places can you measure out to? And if you're familiar with significant digits, if you're multiplying or otherwise integrating numbers together, it's only as precise as your least precise measurement. So if you're taking two measurements, one is in hundredths of an inch and the other is in feet, you can really only say it's precise to feet and not to hundredths of an inch. All right. So that's accuracy and precision. Another important term is metadata. So metadata, simply put, is data about data. And so there's a lot of different types of metadata. Or there's a lot of different um, times when we'll encounter metadata. Metadata are important because it tells you a lot about the data. Different files, different shape files, different layers have can have different metadata. This is a sample from ArcGIS Online, and remember when you click on the layer before you add it, all of the information it provides about that layer, who made it, when it was made, if it was edited, what's the quality, what's the resolution, what's the spatial data, what type of file is it, and so forth. All of that is considered metadata, so it's a description of the data. And it's important to be able to access this. If nothing else, you want to know where your data came from, because again, garbage in, garbage out. So you need to know if you're getting your data from a good source. We'll talk about that as the semester continues, but just FYI, metadata, that's a term that refers to the description of the information about the data. And if you've ever wondered how we get geographic information and how we get spatial data, we use what's called a global positioning system or GPS. You've probably heard of that. All smartphones have a GPS on it now. And what is a GPS? Well, the whole system itself involves the different components, but the GPS itself provides you with location. All right. Um, and there's three segments. There's a space segment, so there's actually satellites. Your phone is actually has a signal, receives signals from satellites and sends signals to satellites. I'm not sure if it sends, but it receives signals from satellites. So there's a little receiver on there, and there's satellites. There's a bunch of them. There's 24 U.S. GPS satellites constantly revolving around the Earth, um, and that's sending signals. And you need at least three satellites, which we'll talk about later, to accurately determine someone's position. That's the space segment, which is in space. The control segment is that we have these stations, and I'll show you a map here in a minute. The stations around the country and the world that where we know the exact location, and they're communicating with the satellites. Sometimes they're updating software, they're looking at the timing of things, and sometimes they'll slightly change the flight path and so forth. So that's the control segment. And then the user segment is if you're holding a smartphone, for example, that's the user segment, right? So that's receiving a signal from the satellite and sometimes the control station. Okay. But there's other things, um, other types of GPS receivers, but that's the most common one we deal with. And just so you know, you don't need to know all this information, but these are where our control stations are around the world. The main one, the master one, is in Colorado. the Air Force Base there, but we have stuff all over the world. And then in terms of features and feature classes, this is a term that you'll see a lot. A feature class think of it as a layer in GIS, right? So a point layer, a line layer, polygon layer, attribute layer, that's a feature class. All right, so the primary types we have are points, lines, and polygons, which we've talked about, but also annotations. So if you put annotations on a map, that's considered its own feature class, right? So it's basically feature class is stored in a table, and it shares the geometry, so what polygon, line, or point or attribute, and shares other attributes as well. So basically, uh, something that has in an attribute table, everything in that attribute table combined is a feature class. Whereas a feature is just the individual records, right? So the rows in that attribute table. So um, let's look at an example over here. So how many feature classes are there? So we have four feature classes. We have points, we have lines, we have polygons, and we have attributes or annotations. Excuse me, not attributes, annotations. So those are all individual feature classes. The features are all the individual features. So each point on the map is a feature. Each polygon on the map is a feature. Each line segment on the map is a feature, and then each annotation, so each piece of text is also a feature. Okay, so feature class, just think of it as a layer with a table, with an attribute table, and then each record, which is the row, or the rows, each of those is a feature. Okay. In terms of some of the pros and cons of vector and raster, so the nice thing about a vector is that you can get pretty high precision because as long as you have accurate points, you can get pretty good position. Whereas with a raster, again, you're limited to your resolution, right? So it's always going to be a grid in raster. And so if you're trying to make a polygon or a line or even a point, it's tricky in a raster. You're just going to lose some of your resolution. Tend to have pretty compact file sizes, whereas a raster is pretty heavy, a lot of data. Topology, which we'll talk about later, which is basically like how to navigate around. Um, Coordinate system transformation is pretty easy. So if you want to convert from one coordinate system to another, it's pretty easy in a raster because you just use a mathematical formula, where it's more difficult in a raster. Or sorry, in a vector, it's pretty easy. In a raster, it's difficult. It's also easy to draw large and small objects in a vector, whereas a raster, again, the resolution is really important consideration. Drawback of a vector, it's not continuous, right? So it's all based on points, whereas a raster is really good at continuous data, so temperature data, elevation data, and so forth. So that there's really subtle changes from point to point. A raster is really good at that. Vector is not. Both of these, the rendering can take a little while depending on the amount of data, and both of them can have issues with processing. Yeah, so those are some of the basic pros and cons, and we'll just sort of deal with those as we go throughout the semester. And remember, there's two types of tables. There's an attribute table, which has spatial data, and then we have a standalone table, which is just a DBF file without spatial data. So you can integrate Excel files, for example, into GIS, and it'll store as a standalone table if there's no geographic information associated with it. But all features, points, line, polygons, grid pixels in a grid, and so forth, they all have attribute data, so you can express that in a table. Whereas a standalone is just a table of data. Okay, so I just again want to reiterate that we use coordinate systems for geographic data. So remember, our geographic coordinate system is where the data are located on the Earth's surface. Whereas a projected coordinate system is how to draw a spherical surface, which is, the Earth it's a semi-sphere, it's an oblate spheroid. But so if you want to draw this on a flat surface, you have to project it. So in other words, you lose something when you use a projected system. But we have to do it in order to visualize it on a flat surface. But the geographic coordinate system tells you exactly where something is, and the projected is you always lose something in the projected system. And we talked about, there's a bunch of different projected systems. And I'm gonna just go over this quickly again. Remember, we have latitude and longitude. Your lines of latitude go east-west. Your lines of longitude go north-south. Equator is 0 latitude. We have the tropics, and then north and south are 90 degrees latitude. Longitude, with these lines, you have your Greenwich, right? So the 0 line of longitude goes through Greenwich, England, and then you go east and west, 180 degrees. Okay. Um, yeah, and so normally we express these as degrees, either decimal degrees or degrees minutes seconds. Um, and your degrees minutes seconds will look like this. So like 45 degrees north, 36 minutes, 26 seconds. That's how you'd read that. This would be negative 90 degrees or 90 degrees west, 76 minutes, 1 second. Whereas decimal degrees is a little more intuitive. It's, use a decimal, right? Okay, so we'll leave that there. And that is a review of all the content for week 2.